Spotlight. Yeah, I think that is Steve, can you press on the press that OK? Need to share it. I think it's pretty easy. Some folks are coming.
Okay.
Maybe better to wait.
Yeah. Okay.
Just start here.
Yeah, I'm just waiting until.
I'm just not sure about camera could capture you.
I think it should be fine like that, right?
Okay. We get started.
Yeah, maybe we can wait for 2 minutes.
I think it's good. We can start.
Okay.
Yeah, before we jump. Okay, perfect. Hello, everyone. Welcome to another Safari Live seminar. Today's talk, we have Steve Rhyner. Steve is currently a computer science master student in ETH Zurich. He also did his bachelor study in computer science in ETH Zurich. Steve's interests are in span machine learning systems, artificial intelligence, and data science, and their intersection with computer architecture. Today, he's going to talk about this work, PIM-Opt, the work that he has started when he was a bachelor student here, and then he continued and finished it nicely during his master. And the stage is yours. Feel free to start.
Okay, yeah, thanks a lot, Mohammed, for the kind introduction. And yeah, thanks for giving me the opportunity to give a Safari Live seminar today. And so first, I will present our paper PIM-Opt, which will be followed by a question and answer session. Before we start the discussion, where we will focus on opportunities and challenges to fundamentally scale machine learning training workloads on PIM architectures. So let's get started with the paper presentation. So the name of the paper is PIM-Opt, Demystifying Distributed Optimization Algorithms on a Real-World Processing Memory System, and it appeared at PACT 2024, and it is a joint work with Hao Song, Juan, Muhammad, Jiawei, Ataberg, Harshita, Se, and Onur. So let's start with the executive summary. So nowadays, modern machine learning training is a very data-intensive workload, and processor-centric architectures such as CPU and GPU that are commonly used for machine learning training suffer from the data movement bottleneck, as training samples and models are frequently accessed. Our goal in this work is to understand the capabilities of popular distributed stochastic gradient descent algorithms on a real-world processing memory system to accelerate distributed machine learning training workloads. Our contributions in this work are as follows. So we implement, analyze, and train linear machine learning models on 2 large-scale data sets using distributed SGD algorithms on a real-world processing memory system. Specifically, we use the optimum PIM system as it is available, general purpose, and resembles a distributed system. We demonstrate scalability challenges of the optimum PIM system in terms of statistical efficiency, meaning the number of steps that are required until convergence. Based on our analysis and experiments, we discuss implications for future PIM hardware designs, and we highlight the need for a shift towards an algorithm hardware co-design. And our source code and all our complete code base, as well as all scripts, are open source and available on GitHub. You can follow this link here. In our evaluation, we compare the optimum PIM system to state-of-the-art CPU and GPU architectures, and we conducted a study for the JFCC 100M data set, which is from Yahoo, where we observe that the optimum PIM system is up to 1.9 times and 3.2 times faster compared to the CPU and GPU baseline, respectively. And we also studied the Criteo data set, where the optimum PIM system is up to 9 times and 10 times faster compared to the CPU and GPU baselines. As an example for the scalability challenges that we observe on the optimum PIM system, for the Yahoo data set, we observe a speed up of 7.4, while the achieved test accuracy decreases from 95.5% to 92.2% as we scale the number of nodes. We will discuss in more detail why this is the case. Here you can see an outline of the talk, and yeah, let's start with the background. So 2 of the most commonly trained linear binary classification models are logistic regression and support vector machines. And the overall goal of machine learning training is to find an optimal machine learning model by minimizing an objective function or a loss function over a training data set. And it is common to deploy regularization techniques in order to prevent overfitting on the training data set and to control the model complexity. Stochastic gradient descent (SGD) is perhaps the most important and commonly deployed optimization algorithm for modern machine learning training due to its simplicity effectiveness and generalization performance. And SGD is the main building block of most distributed optimization algorithms. Variants of SGD, such as mini-batch SGD, allow for parallelization by batching training samples in each iteration. Distributed optimization algorithms can be categorized roughly in two categories. One are centralized algorithms, and the other are decentralized algorithms. And for centralized optimization algorithms, we have the underlying topology is a centralized topology where we have a parameter server, or also kind of a decentral node. We have many workers, and all the communication happens via the parameter server. In the case of decentralized optimization algorithms, we have a decentralized topology where we get rid of the parameter server and remove this communication bottleneck on the busiest node and allow for communication among the nodes. Popular centralized optimization algorithms are mini-batch SGD with mul averaging, MASGD, mini-batch SGD with gradient averaging, GASGD, and distributed alternating direction method of multipliers, ADMM. This picture shows the real-world UpMem PIM system that we use in our study. It consists of standard CPUs, standard DRAM modules, which coexists with UpMem PIM-enabled memory. Let's now look into how the UpMem PIM system architecture looks under the hood. So we have the host CPU with multiple cores and memory controllers, and we have these main memory modules, which are DDR4 modules, as well as the UpMem PIM-enabled memory modules, which have the same form factor as the main memory modules. And the communication takes place via DDR4 channels. Each UpMem PIM module consists of two UpMem PIM ranks, which in turn consists of 8 UpMem PIM chips, and each UpMem PIM chip has 8 banks. And within each bank, there's a DRAM array of 64 megabytes, which is called main RAM or MRAM. And there's the DRAM processing unit, which is abbreviated by DPU, where we have an instruction memory, as well as a working memory of 64 kilobytes, which is abbreviated by WRAM, and this acts as a scratchpad memory. And there is an in-order fine-grained multi-threaded pipeline, which implements a 32-bit RISC-based instruction set architecture with native support for 32-bit integer additions and subtractions, as well as 8-bit integer multiplications. However, more complex operations, such as 32-bit integer divisions and floating point operations, need to be emulated through software. We also have a high bandwidth internal data bus. And maybe here's a good place to note that all the inter-DPU communication takes place via the host CPU. So there's no interconnect between individual DPUs. Next, I will talk about the motivation of our work. So nowadays, the key problem that we're facing is the data movement bottleneck. Since most architectures nowadays are following a processor-centric design, which are highly imbalanced systems. So we have the CPU with on-chip memory, such as the L1 and L2 caches, and yeah, we also have a DRAM and hard drives for larger storage. And every time, and the imbalancedness stems from that all computation happens on the CPU, and every time we want to operate on data, we need to move it all through this memory hierarchy. And this the processors have become overly complex in order to hide the load and store latencies. And applications have become increasingly data hungry. And furthermore, stochastic gradient descent is a memory-bound algorithm. So the data movement bottleneck is a key limiter of large-scale machine learning training. And processing memory is a promising solution to perform large-scale machine learning training, as it alleviates the data movement bottleneck by placing compute units inside or near memory. But how do we start? By identifying key characteristics covering the design space of both hardware and optimization algorithms. In order to understand why it is important to carefully choose the optimization algorithm that best fits the optimum PIM system, we look at the measured throughput for the distributed optimization algorithms, and we look at the communication with the parameter server and PIM. So the parameter server being the host CPU, and the throughput that is the aggregated throughput that is achieved within PIM, so aggregated over all DPUs for the MRAM, WRAM transfers. We also look into the total data movement. And for instance, the ADMM algorithm within PIM, we have 64 times higher throughput compared to the communication with the parameter server. And for the optimization algorithm, GASGD, it's 64 times. So the goal should be to minimize the communication between the parameter server and PIM as much as possible. And for the total data movement, for instance, MASGD requires 64 times more data to be moved between the optimum PIM-enabled memory and the host CPU compared to ADMM. And compared to GASGD, it's even over 1,500 times more data movement. So we want to minimize the total data movement between the parameter server and PIM. So the communication efficient ADMM optimization algorithm is attractive for distributed machine learning training on the optimum PIM system. And it shows that it is important to carefully choose the optimization algorithms that best fit PIM.
So I have,
Mohammed?
Yeah, I have some questions. So can you get back to the previous system? So about this algorithm ADMM, that is actually, you are saying that is a good fit or best fit for optimum PIM system.
Yes.
Can you also generalize that? Is it also the case for PIM system in general, or this is really focused for optimum? So
also for Samsung's HBM PIM and SK Hynix's accelerator in memory, this is also the case, yeah, that we can leverage kind of like the communication efficiency of ADMM, which is, yeah, algorithm specific to the algorithm itself.
Okay, and so in this work, you're trying to assess the training, I mean, the performance of doing machine learning training on optimum PIM systems.
Exactly, yeah.
So there has been work on assessing machine learning training on PIM system in general. So how do you compare? Maybe it's too early to ask that question, but I like to ask it because we're in the motivation. You know? So how do you compare your work with those works, essentially?
So in prior work, other prior work either don't consider real-world PIM systems, and there's another prior work that considers gradient descent. However, this is not a widely used algorithm in the machine learning community, as it is very computationally intensive, due to since in order to update the model, we need to pass through the entire training data set. And also this work addresses the resemblance of the UPMAN PIM system to the resemblance as being a distributed system.
Yeah, and you're using stochastic gradient descent.
Exactly. Yes.
And okay, and with that you don't need to go over the whole training.
So with stochastic gradient descent, so more precisely mini batch SGD, we alleviate this this computational bottleneck by since in each iteration before updating the model, we only need to process a few training samples or a batch of training samples, which is a subset of the entire training set, so at a time.
Good. Any other questions?
Okay. So yeah, thanks for the questions, Mohammed. So now, how do we map the distributed algorithms to the UPMAN PIM system? So in this diagram, we show the host side on the left with the host CPU, and on the right-hand side, we show the workflow on the DPUs. So first of all, the host CPU distributes partitions of the training data to the DPU's MRAM, and this happens only once during the entire execution of the program. Next, the host CPU invokes the DPU kernel, and each DPU starts running the same program, which in this case is an SGD optimizer. And in order to synchronize, to perform inter-DPU synchronization, the local models and gradients are aggregated on the host CPU, which and once the updated model is computed, the updated global model is broadcast back to the DPUs, and this flow is repeated until convergence of the model.
Sorry.
Yes.
Just for me to understand better. So essentially, each DPU is calculating some local gradients, and in that inter-DPU synchronization, you need to combine them.
So for instance, for the algorithm gradient averaging SGD, the entire batch is distributed among all DPUs, and each DPU computes an intermediate gradient, which is then communicated with the host CPU, which adds the gradients, aggregates the gradients, and performs the update on the global model. For model, and the issue with gradient averaging SGD is that every time or for every batch, we need to perform this inter-DPU synchronization. Instead, for model averaging SGD, we can have an entire pass on the training data that is located on the DPU, updating the local model, and then the local model is aggregated on the host CPU, where the global model is calculated and broadcast back to the DPUs.
I see.
Thanks for the questions, Mohammed. And in order to unleash the task parallelism, we have that every DPU is a worker. And for each GPU, we use 16 tasklets collaboratively to implement the mini batch SGD optimizer. We use 16 tasklets in order to fully saturate the pipeline on each GPU. And the features of the train samples and model parameters are evenly distributed among tasklets. We used lookup table-based methods for training of logistic regression, which involves computing the exponential function in order to evaluate the sigmoid activation function. And we use these lookup tables since the Upman PIM system does not support transcendental functions. And we specifically use the transpim-lib library to have a very efficient lookup table-based computation and evaluation of the sigmoid. So next, I will briefly talk about the methodology. So the systems that we use in this study are the Upman PIM system, which for which we have server-grade processors, as well as 2,560 DPUs running at a clock speed of 350 megahertz. And in total, there is 160 gigabytes of Upman PIM-enabled memory. For our CPU baseline system, we have two high-end AMD EPYC 64-core processors. And for the GPU baseline system, we have high-end processors as well. And the GPU that we use is an NVIDIA A100 GPU with 80 gigabytes of GPU global memory. For our CPU baseline implementations, we use PyTorch as it is widely used in the community, and it's highly optimized library. And we implement model averaging SGD, gradient averaging SGD, and ADMM to train the models logistic regression and SVM using and leveraging the optimizers and communication libraries that are provided by PyTorch. We consider each CPU thread to be a worker. And for the GPU baseline implementation, we use PyTorch as well. However, we only implement mini batch SGD on the GPU as PyTorch does not provide a way to limit the amount of GPU resources the kernels use, which causes model averaging to be serialized on a single GPU. And for fair comparison, we do not consider a cluster of GPUs for our baseline because the Upman PIM system is a single server node. For more experiment implementation details, I would refer you to our full paper that is available on arXiv. So are there any questions?
Any questions?
Okay.
I have one. Actually.
Okay. Yeah.
So you mentioned you use 16 tasklets
yes.
per DPU. First of all, I mean, is there a particular reason for that?
So we should use, so a previous study has shown that we should use at least 11 tasklets to saturate and use the entire pipeline. And why we use 16 tasklets is more kind of from an engineering perspective, as it facilitates basically the distribution to distributing the work between the tasklets.
So is that the only reason? It's not about like did you perform some experiments to show the optimum point for how many tasklets we need to use? I understand about 11 because,
okay.
But something between 11 to, I guess, 28 is the maximum number. I don't remember. 24.
Yeah, 24 is the maximum. So yeah, I also ran experiments with 16 and 24 tasklets actually, but I did not see any huge gains this would give us. And yeah, due to the experiments being very large scale and taking a long time, I decided to focus on 16 tasklets.
Okay. Thank you.
Okay, yeah, thanks, Mohammed.
So I have a follow-up question.
Yeah.
So basically, for each tasklet,
Can you ask a bit louder, such that
okay. So basically, for each tasklet, what's the local cache size that you need to use for your experiments?
What do you mean by local
So basically,
cache size?
I'm asking the question that you need to fetch the data from MRAM to WRAM, right?
Yes.
Now, for your performing the computations in batches, as you have multiple threads, each thread needs to allocate some data, right? So that you're performing computations on that.
Yes.
So what's that amount of chunk that you're performing your computations on?
So what we're doing is we basically distribute features of a single training sample and model parameters to each tasklet. For YFCC, which is a smaller and dense model, we can actually keep it in WRAM and don't need to move it around all the time. However, for Criteo, which has a size of 4 megabytes, we actually need to move it back and forth all the time, which makes it too small. But we could also, like, another approach we could take is to give each tasklet one training sample at a time. But yeah, I found that this incurs even more data to be transferred, as I want to keep the model in the working RAM as much as possible. Does this answer your question, or?
Yeah, it partially answers.
Okay, and what part did I?
I mean, I was just looking for that size. So it is also possible that your WRAM size was not enough, so that you will not be able to go beyond the threads that are available, or it's like it was enough available in the WRAM space.
Yeah, so WRAM was kind of like a limiting resource, but yeah, the more tasklets we have, kind of like the less features we need to allocate for each tasklet. So yeah. Kind of.
Okay. Yeah, sounds
good. Okay.
Thank you.
Okay. Yeah. Thanks. So yeah, let's now look at at our evaluation and some key results. So for the Yahoo data set, we have a relatively small but dense model of around 4 kilobytes with around 4,096 features. And yeah, let's now look at how the UpMem PIM system performs in comparison to other architectures. So in this figure, we look at the total training time and evaluate the test accuracy for both models, logistic regression, and SVM for the gradient averaging SGD algorithm. For the architecture, for the PIM architecture and the CPU architecture. And we observe that GASGD on the UpMem PIM outperforms GASGD on the CPU for both logistic regression and support vector machines. So for instance, the CPU baseline requires 1.6 times more time compared to the optimum PIM system, and for SVM, it's a factor of 1.9. And yeah, this difference in training time for from logistic regression and SVM stems from that SVM has lower computational complexity, which is beneficial for the optimum PIM system. Now let's compare the optimum PIM system to the GPU architecture running mini batch SGD. So here, GASGD on the optimum PIM system outperforms mini batch SGD on the GPU for both models. So the PIM system is 2.7 times faster compared to the GPU. And for the support vector machine, the GPU baseline system requires 3.2 times more training time. And for other algorithms, such as MASGD on the optimum PIM system, so MASGD on the optimum PIM system significantly outperforms MASGD on the CPU for both logistic regression and support vector machines. And for ADMM on the optimum PIM and on the CPU, there's a comparable performance for both models. So the optimum PIM system is a viable alternative to the CPU and GPU architecture for training small, dense models on large-scale data sets.
Okay. How would PIM affect the accuracy, this test accuracy?
So maybe I'll come to that in 2 or 3 slides. So okay. Yeah, maybe let's hold that question. Yeah, sure. Yeah, okay, thanks. So now to understand key characteristics of distributed machine learning training on the optimum PIM system, looking at the logistic regression support vector machines for all optimization algorithms we study, we break down the per global epoch training time into the time for communication synchronization with the parameter server and the fraction allocated to PIM computation, as well as to PIM data movements, so the MRAM, WRAM transfers. So the communication and synchronization between the parameter server and PIM is a bottleneck for MASGD and GASGD. So for instance, MASGD has 223 times more requires 223 times more time for communication synchronization between the parameter server and PIM compared to ADMM. And for all combinations of optimization algorithms and models, PIM computation takes more time than PIM data movement on the optimum PIM system. So for the SVM model, the PIM computation requires 14 times more time compared to the PIM data movement. So the optimum PIM system is less suitable for machine learning models and optimization algorithms that require frequent communication and synchronization between PIM and the parameter server. So now let's look at the study for the Criteo data set, for which we have a sparse and larger model of around 4 megabytes. So to assess the scalability potential of the optimum PIM system, we scale the number of GPUs from 256 to 2048, while we keep the training data set size fixed. And we compare optimization algorithm for both models and how this impacts the total training time, as well as the AUX score. So for high-dimensional sparse model for model averaging SGD and ADMM on the Optimum PIM system, we observe good, strong scalability in terms of total training time, but poor in AUX score. So for instance, for MASGD, as we scale the number of DPUs, there is a reduction by a factor of 2.9 in terms of total training time. However, the AUX score decreases from 0.74 to 0.72. So I guess here also, this is a good place to answer your previous question.
Yeah, but before that, maybe I missed, what is the strong scaling?
Strong scaling is as we scale the number of nodes, here the DPUs from 256 to 2048, we fix the training data set size as we scale the number, as we scale the number of nodes.
So each DPU will get less data, essentially.
Essentially, yes, yeah.
Okay, now about error.
So about error, so as we have more DPUs, this directly corresponds to more models, and more models increase the staleness as each DPU works on its own local model, and this tends to overfit. And yeah, this is a reason why we see this reduction in error.
Mm-hmm. Meaning that for CPU also, if we use a higher number of cores, that can also affect accuracy, right?
Yes, exactly. So for our CPU baseline, we use 128 models, CPU threads. So yeah, this also affects. Yeah, so it's a trade-off between performance and accuracy.
So the reason I'm asking this is that it's not related to PIM system. It's related to how many compute engines you're gonna use, right?
That's
like if you use for CPU, if you have 1,000 cores, then you're gonna also see different accuracy, right?
Yes. Okay. Yeah.
Any other questions? And let me check YouTube just to be sure. Okay.
Okay. Yeah, thanks for the question, Mama. So from this observation, we know that the scalability potential of the Optimum PIM system for training high-dimensional sparse model is limited by its lack of direct inter-GPU communication. And in the paper, we have a rigorous analysis of many combinations of algorithms, models, architectures, and data sets. And for each of the data sets, we explore the PIM performance breakdown, PIM performance comparison, and algorithm selection. And we conduct a batch size sensitivity analysis and the impact of scaling, for which we have two different variants, such as weak scaling and strong scaling. So I explained earlier how strong scaling works, but for weak scaling, basically refers to when we scale the number of nodes, and meanwhile, we also proportionally scale the training data set size. We also have extended observations, takeaways, and discuss implications for future PIM hardware designs. Yeah, we have much more information in our paper, which you can access on arXiv. So what, do you have any questions? Yes.
Inter-GPU communication seems one of the major problems in PIM systems.
Yes.
What is the biggest problem in improving?
how do you mean in improving it? Like
to enable it.
To
enable it, basically.
To enable inter-DPU communication.
Exactly.
So I don't know what the problem is. I mean, it seems like a quite simple solution to just add interconnects to the DPUs instead of having to go to the host CPU for inter-DPU synchronization. So maybe Mohammed, do you think like these interconnects are feasible to add to processing memory architectures?
So when I mean interconnects can be of course feasible to add, and there are actually some recent works that people also try to propose such interconnect for open PIM system. But yeah, in the end, it's the matter of I would say designer choice, because you have a limited amount of resource, and then you decide, what to add or what not to add. And for some reason, they decided for that edition to not include interconnect. But in my opinion, also that's a must. I think at some point they really need to add it. But of course, interconnect consumes power, consumes area, but other things also consume power and area.
Yeah, definitely. I mean, it seems just like an obvious limitation, the micromain system. That's why I asked.
Yeah.
And probably you don't even need, like, you can use, for example, I just assume that for this machine learning applications, you would just need specific interconnects so that you could maybe even reduce, instead of interconnecting, let's say, in my mind, many DPU cores, just connecting some of them would already give a large improvement in performance.
I mean, these applications usually they actually need quite simple interconnect, because in the end you are doing some reduction, right?
Yeah.
And it's very regular,
So
even in one DPU, like in one memory chip that we have
yes.
several DPUs, right?
Yes, in each UpMem. Sorry, what?
So in one memory, like this DRAM bank, we have several DPUs, right?
Yes, we have 8. Yeah.
And we have done these works like row clone, that we can communicate data across banks. So with that, actually, we can easily implement at least synchronization across the one DRAM chip, right? That it has like 8 or 16 DPUs, right?
Yeah. So one UpMem PIM rank has 64 DPUs in total, and one entire UpMem PIM module has 128 DPUs.
So one rank has 32. 64.
And
each 8. Of them also we have a few, right?
So we have in each UpMem PIM rank we have 8 UpMem PIM chips. So in total for each UpMem PIM chip there are 8 DPUs.
Yeah, that's what I'm saying. Yeah. Like in each UpMem chip, we can at least provide communication using row clone techniques, for example.
What is the position of UpMem on this? Like, have we ever raised this point to them? Or
yeah, of course.
What is their point?
So actually, I guess Fabrice, I'm not sure if I pronounce his name correctly, but he actually gave us a Safari Live seminar in the past, and we actually asked that question, and he basically brought up the issue of interconnect, which is power, thermal, and those stuff. But in my opinion, that's not satisfying, let's say, enough, because other things also consume. So in the end, it's a designer decision and trade-off that they care at that moment, I guess.
Thank you.
Okay, yeah, thanks for the question.
So overall, for your application, from this application perspective, you're more limited by not having a multiplier, right? Or rather than a communication bottleneck.
Yeah, I mean, both would be nice to have.
Which one would be, according to you? I mean, we don't have numbers, but according to you, which one will be the most dominating factor?
I mean, it's hard to say. I think like having a more capable multiplier would definitely speed up things, and would also maybe allow for floating point operations. which for machine learning training, yeah, we would like to have that. But kind of like the having inter-DPU communication with direct on-chip interconnects would enable us to implement other algorithms, which have been shown to scale much better than centralized algorithms. Okay, thank you for the question.
Those were good questions. Any other?
Yeah. So you already took away some points. So yeah, so what are the implications for future PIM hardware design? So our evaluation demonstrates that real-world PIM system can be a viable alternative to state-of-the-art processor-centric architectures for many distributed machine learning training workloads. And we argue the most simple change that future PIM architectures should add interconnects and/or shared memory among PIM processing units, as it would enable to implement decentralized optimization algorithms, and more specifically, decentralized parallel SGE algorithms, which are a promising solution to overcome scalability challenges of the real-world PIM system. Yeah, one major advantage of decentralized algorithms is that we remove this communication bottleneck on the busiest node, which would be the central node. And we posit that a shift towards an algorithm hardware co-design perspective is necessary in the context of machine learning training using processing and memory due to the high complexity of the entire design space from hardware design to algorithm design and many, many more. So I will now conclude the paper presentation. So we evaluate and train linear machine learning models on large-scale data sets with centralized optimization algorithms on a real-world PIM system. And we show that it is important to carefully choose the distributed algorithm that best fits the real-world PIM system, and we analyze the trade-offs. We demonstrate that commercial general purpose PIM systems can be a viable alternative to state-of-the-art processor-centric architectures such as CPU and GPUs for many distributed machine learning training workloads on large-scale data sets. And our results demonstrate the necessity to adjust PIM architectures to enable decentralized parallel SGD algorithms to overcome the observed scalability challenges for many distributed machine learning training workloads. Yeah, there's a lot more potential and a lot more research that can be conducted in this area. For instance, considering larger models and what changes in terms of hardware and maybe also algorithmic changes need to be there need to be changes. And also these new compute paradigms and accelerators require us to rethink the entire stack from the algorithm down to the hardware design. And here are the QR codes where you can access our archive paper as well as our entire code base and all our scripts on GitHub. And I'm happy to take more questions now before we move to the discussion.
Can you explain a little bit more about decentralized algorithms?
Excuse me, about what?
Decentralized.
I didn't hear.
Yeah. So for decentralized algorithms, we Like,
so those are already implemented for other systems, right? For GPU.
Yes. I mean, for the UpMem PIM system, it's just not feasible because it does not make sense to implement them on the UpMem PIM system, as we do want DPUs communicating with their neighbors to enable these algorithms.
So with these centralized algorithms, you have one, basically, like there is a node that everyone needs to communicate with that.
Exactly.
And in UpMem system, that's actually the whole system, right?
Yes. So in the UpMem PIM system, this is the host CPU where the entire orchestration and synchronization takes place. And ideally, for decentralized algorithms, we would not need kind of like this host CPU, or maybe in a more limited way.
Yeah. Okay. And essentially, there might be a lot of communication across DPUs that can in decentralized algorithms. And again, lacking interconnect is the main limitation.
Yeah, this is the key limiter. To really being able to implement decentralized algorithms.
I see. Question?
Yes.
It's not related to the main idea of your work, but so I'm unsure about the software infrastructure around the real-world processing network system. So how do you write the programming code for AppNet?
Can you maybe repeat the question?
So I'm not sure about the software infrastructure regarding AppNet. So how do you program?
So basically, the entire code is written in C programming language, and there are like supporting libraries from like the UpMem SDK with kind of like minimal support for kind of like broadcasting data to the DPUs. However, the whole software stack is not really existent for UpMem. So basically all optimizations need to be engineered, and kind of like there are not really high level abstractions provided.
So you have to manipulate, optimize a memory access pattern.
Yes, you basically need to orchestrate memory accesses and all the computation, and kind of like also time everything.
So how much more effort required is it to write programming code for AppNet compared to CUDA or OpenMP for CPU or GPU?
So I would say it's similar to CUDA programming. However, for CUDA we have like more support. However, for CPUs, in general, we just use PyTorch, or kind of like, which abstracts away the complexity of the programming.
PIM programmability is actually one of the exciting research topics. For UpMem system specifically, we have also done a work named Simple PIM. I guess you're aware of that, right?
Yes.
That that designs is a library essentially that we can use to implement some of these synchronization primitives, I guess.
Yes.
Also gather, scatter, I guess those are implemented.
Yeah.
So you mentioned we can use the decentralized algorithm to increase the scalability. So why we don't just increase the number of master server? I mean, the parameter server.
Yeah, that's.
Can you repeat the question?
So yeah, so in the audience, there was a question regarding the scalability of the UpMem PIM system and whether this scalability could be improved by adding more master nodes or central nodes. And the answer is yes. And this would also be kind of like a good starting point for our discussion later, as it already touches on the first discussion item. So yeah, let's maybe move to this first discussion item. So you already mentioned that we could maybe have more master nodes or kind of like more central nodes, and yeah, and to alleviate this communication bottleneck. So one thing that could be done is to each UpMem PIM rank, we could add a more capable DRAM processing unit with a large shared memory unit, which would basically enable us to also reduce the number of models and kind of like, yeah, move this central node closer to the DPUs. Okay, I don't know if this was understandable or, but it kind of like relates to your question or idea to.
So what do you mean by a large shared memory unit?
So
basically, where you are envisioning to add this shared memory?
So I'm envisioning to add like a larger shared memory unit to each UpMem PIM rank, which could also yeah, allow for larger models to be trained. Yeah, instead of like right now we're quite limited in the size of the model. So yeah, since the MRAM is only 64 megabytes, so if we have a model that is larger than 64 megabytes, yeah, we would have to yeah, always reload the model into the MRAM, and with a larger shared memory unit, we could host larger models.
Yeah, but how does alleviate communication overhead?
So I mean, there still will be communication overheads, but we don't yeah, need to wait. Basically, do everything on the host CPU, but can kind of like asynchronously yeah, perform the training.
Mm-hmm. So currently, DPUs. So are DPUs sharing a memory? The main RAM is shared.
So the MRAM, this is yeah, each DPU has one MRAM.
Yes.
And they're not shared.
They are not shared. So with this shared memory, all DPUs within that rank, they can access that, right? Potentially, they can use that for synchronization, right?
Yes, exactly. So yeah, also yeah, the whole orchestration and yeah, synchronization. Yeah.
Yeah, that can reduce data movement bottleneck some. to some certain point.
Yeah, maybe.
Because for synchronization across DPUs, you don't need to go to the CPU. You can
Yes.
use this memory, right?
So yeah, it would kind of like move the data again closer to where we actually perform computations.
Mm-hmm. But now the programming might be a bit, in my opinion, harder because it's mixing shared memory paradigm and message passing paradigm, no? Because the current implementation is not in shared memory paradigm, I guess.
So yeah, this would be certainly a key challenge that would add to the programmer, or ideally there would be some kind of library that abstracts this away for the programmer. Mm-hmm. And yeah. Yeah.
But how you're envisioning to interconnect these large shared memory across DPUs? Because they need to access it, right?
Yeah. Yeah, I'm not sure. I mean, this is like for the hardware designer, so to figure out. I mean, it would be nice to have it. So yeah.
Okay.
So this is maybe just because I'm not totally familiar with the topic, but what I'm always wondering is, like, proposing such solutions, how do you keep in track if it doesn't increase overheads, like intuition-wise in your head? Because like obviously like increasing the memory, the shared memory, etc. would be nice, but then we also not have significant overhead in having to track all of this stuff that you introduce, which then might impact the system performance.
Yeah, you're absolutely right. There might be other overheads that we might not think of right now, and yeah, this certainly needs another study on how such ideas could impact the performance, and or kind of like what trade-offs there are and how they could be addressed, or if it even makes sense to have this shared memory unit. Yeah. Does this answer your?
Yeah, I mean, it was a bad question anyway, but that was just trying to have basically an intuition on.
Mm-hmm.
Yeah, but I guess it's difficult. Obviously, it's a difficult question. But thank you.
Yeah, thank you. So, do you have any other questions? So then let's move on to the second discussion item. So where we observed that models frequently accessed and updated during machine learning training, while training samples are accessed less frequently. So could we leverage this observation to further reduce the synchronization and communication overheads of PIM architectures? Do you have any ideas? Do we have something on the Zoom chat? Okay, yeah, we have a question.
Yeah, oh, it would be an idea.
Okay, yeah, an idea.
One idea would be to add a specialized cache or something like they do on GPU for textures. They use a texture cache.
Okay.
Or something, maybe specialized cache for a model.
Okay, yeah, that would, that's also a solution option that I had in mind. So to have separate memory units for the training data and the model, but can you also think of challenges that this might bring? Yeah, so it of course increases the complexity, and another problem could be, yeah, that applications in general have varying model sizes and training data set sizes. So it's again another trade-off that we would have in deciding how large these memory units should be, what kind of characteristics they should have. So yeah, maybe does anyone have anything to add to this idea? Yes.
So what I was thinking about a few months ago was some method of like continuous learning, basically meaning that you have a model and then you don't stop training it, but you retrain it with new training data that is constantly coming in and so on and so forth. Because my key problem with this is, in this scenario, the normal training samples would need to fit in memory, right?
Mm-hmm.
Yeah, but that if I assume now that my training data size actually comes batch-wise, like my sensors collect data, for example, in computer vision, they come and then I train, and then I train, and then I train. I actually feel like this could be quite useful now, because like if you can regulate the size of the training data accordingly.
Yeah, that's a very good idea. So basically to have like a large memory unit that can host the model, and kind of like a memory unit that can act as kind of like a buffer. Yeah, that's a good point. Does anyone want to add something to this? Mohammed, do we have a question on the Zoom chat?
Yes, I had a question, but it was on a topic that was much earlier, so I will just ask it now. So on the topic of provisioning network interconnects for processing in memory, one of the use cases where we can perform these reductions much more efficiently in memory. Do you think computation in network could also be another benefit here, especially because we want to perform reductions, and that's a very simple computation? So the question is in two parts. Can we do this theoretically? And second is, if we do it, is it practical enough? Thank you.
Yeah, that's there are interesting questions. So theoretically, if this is feasible, I'm kind of like not sure, because yeah, it again is we have this design choice and trade-off on how large or like how capable these computation in network should be, and kind of like also what kind of topology should we support for the interconnects. So I think this could have some value, but it also adds a lot of complexity for the programmer. So I'm not sure how practical this consideration would be. But yeah, maybe someone else can comment on what their thoughts are, whether having computation on the interconnects would be beneficial. So yeah, I think this answers your question only partially. But
yeah, that's all right. That's all right. Thank you so much.
Okay, yeah, thank you.
I was just thinking more along the lines of, because it would be simple computations, it may not be really expensive to implement. but then the only concerns are how much power this would require. Yes, but I agree with you in the sense that it's kind of difficult to evaluate these things. So yeah.
Okay. Yeah. Thank you for these questions. Yeah, it's definitely something that one could look into for a different study. Yeah, as there are this again adds complexity to the entire design space. Yeah. Thanks.
Yeah, I agree. Thanks.
Do we have more questions on the Zoom?
No.
And on
Oh,
YouTube? Okay. Yeah, then I would like to move on to the third discussion point. So how could we enable deep learning on PIM architectures? So yeah, do you have any idea what would be needed in order to enable deep learning?
What's the main challenge?
I mean, there are many challenges. So yeah, there are more challenges than solutions. Yeah. But yeah, can someone think of any challenges?
So first of all, with PIM architectures, do you mean augment PIM system or general?
So I would like to yeah think of like more general PIM architectures, and it does not need to be UpMem specific.
Because I guess there has been works on deep learning on PIM systems, general PIM systems.
Mm-hmm. Yeah, so one key challenge.
Yeah, it's related to UpMem, right?
Yeah, that's yeah. Okay, yeah, okay, then related to UpMem. Yeah, the mapping of the model. But this is also a challenge for other architectures, I guess. Yeah, how to map the model, and kind of like how do we place each layer of the network, yeah, and how to assign these to the processing units. Yeah, and kind of like how should we distribute the layer across processing units, or should each processing unit be responsible for a single layer? And yeah, there's another challenge that comes with this. So deep learning, yeah, there are a lot of different models, and they vary in size, and each layer can potentially be much larger than the previous, or than other layers in the network. So it's kind of like hard to really assign, yeah, kind of like have a hardware design that addresses that. And also, how should the forward and backward pass be orchestrated, and how could we prevent underutilization of the hardware resources, as yeah, due to the sequential nature of network, and yeah, what granularity should the training data be placed, and also the training samples and the features, and kind of like how should the tasks be distributed. Yeah, does anyone have any thoughts on this? Yeah.
So I was just curious that with deep learning on PIM architecture, you're only referencing to training, right?
Yes.
Because,
so
like, I was wondering why you didn't make the difference between training and inference.
So yeah, so we're mainly focusing on training. Yes, as for inference, we can actually like have we do have the model, and we can like just have a limited amount of new test samples that we want to perform inference on. However, for training, this is requires a lot more computation and and memory for the training data. So it's these are kind of like very different. So machine learning training is inherently different from inference.
Definitely, I agree. But what I wanted to say is basically, I just imagined like some problems obviously would be inherited, like mapping of the model and the varying size of the network layers. But still, there could be benefits of doing inference with processing memory architectures, no?
So yeah, there also have been many more works on inference with processing memory architectures.
Oh.
Yeah.
I was just confused because it didn't say in the discussion.
Okay. Okay. Yeah. Sorry for the confusion. Yeah. Okay. Yeah. Thanks for the input. So rethinking this design space of PIM architectures to enable deep learning training remains a key challenge. And there's a lot more work to be done, and a lot more potential there. Does anyone have any further questions? So, okay. I guess this would then conclude the seminar. And thanks all for your questions and input. And also a special thanks to all the collaborators of this work, Hasong, Juan, Muhammad, Chiawei, Ataberg, Harshita, and Tse and Honor. So thank you very much.
Thanks you. Any other questions? Okay, perfect. Then we can end today's session. Thanks a lot.